All right. So we look today into a Newton's method. We already know about the one-dimensional Newton's method. Okay. Today we will look into the n-dimensional case. We will extend that method into n dimensions. Okay, and we'll also apply the Armijo condition. So what we had regarding the Newton's method of optimization, can anyone say? Xk plus 1. This is just one-dimensional. So I'm not treating x as a vector. So xk plus 1 equals to xk minus is it okay? No, it's not still okay. This you know xk plus 1, this is xk, but f is a function of x also. So at which iteration you will solve it, you did not mention. So you have to solve it at xk iteration. At that value you have to solve. Else it creates confusion whether you will solve at xk plus 1 or xk if you don't mention it. So maybe like better way to write this is in multidimensional case, like this is just for 1D, this is 1D case. In multidimensions, multidimensional case, so x, just x, this x is getting translated to like x vector. Is it okay? X vector. So, so the formula will now involve vectors. So xk plus 1 equals to vector x at k with iteration. Then what shall we write? So we have to find an analog of this derivative in higher dimensions. And what's the derivative? Analog in higher dimensions? Gradient. Okay. The analog of derivative in higher dimension is like gradient. So if you write gradient here, so I'm saying that you replace f prime with a gradient. So can you say the method to me? I will write the method, but so gradient will be a matrix, isn't it? Gradient of f like is a matrix. Okay, so here is a matrix also. Here it's a matrix, like it's a column vector. It's a special case of a matrix. This is also a matrix. So the right side also should be a matrix. So how shall we develop this method? I don't want to write. I want to develop your thought process. Then write. Can anyone say the minus sign is there? Okay. Then correct to write like this. Is it correct to write? Why? See, grad f prime, I replaced it with grad f divided by f double prime, that is grad 2f, okay, second Hessian, and I took the inverse because it's in the denominator, it shifted to numerator. All these things, I should have written like here xk, it's evaluated at xk. So now you know, so similar to 1D, the method, as we know in Newton's method, it's heavily dependent on initial conditions, isn't it? We saw fractals. We saw how complicated it is, like with respect to initial conditions. A small change in initial condition can lead to a different output. So therefore, Newton's method in 1D depends on the initial conditions. So similarly, for higher dimensions also, it's true. Okay, which point in space you will take your initial condition matters for this method also. And even Newton's method is like not that efficient for highly nonlinear functions like cosine e to the power x, sine x, and lot of complicated functions you can't put it and expect a accurate answer. So usually like how to improve the convergence. Some of the limitations of Newton's method in higher dimension and one dimension. So how to improve the convergence of Newton's method? What shall we do to improve the convergence? Yes. So to improve the convergence, as previously, we will apply the Armijo condition to Newton's method. Okay. So to improve convergence of the Newton's method, to improve convergence, apply Armijo condition. Okay. All right. So this is the Armijo condition for you. It's exactly similar to this only, but let me write the proper way. Like xk plus 1 equals to xk. It is very similar. Minus just the step size. Okay. Grad 2f inverse grad f. You see, just the same idea we borrowed from gradient descent. Same idea. How? In gradient descent with Armijo condition, we told that if the Armijo condition is satisfied, it is okay, continue iteration. If Armijo condition is not satisfied, then decrease the step size by tau. H was going to tau h, isn't it? Tau was belonging to 0 to 1. Yes. So we decrease the step size. So here also, it is saying xk plus 1 is xk minus h. That's the step size. Del 2f inverse del f, like grad f. Okay. So h is the step size here. For usually we take h equal to 1, and till now h equals to 1 solves the problem. Most of the problems. If you take h equals to 1 and iterate your problem like method, it is getting solved. Okay. But if it is not solving, like it takes a higher lot of iterations, then you can change your step size. H going to again tau h. Okay. So that way it is a variant of Newton's method from a perspective of Armijo condition. Okay. Usually take h equals to 1, and still it will easily and nicely converge. Okay. In my I will share the code with you. There I have taken step size equals to 1 and Newton's method. Please go through it. Okay. Just step size equals to, so find in the code where I have written step size equals to 1. That's your task. Find in the code where I have written step size equals to 1. That's exactly the Newton's method. All right. So till now, like we discussed, this is for the multidimensional Newton's method. All right. And this method will lead to creation of several other methods of optimization known as quasi-Newton method, which I think in the project we will hear. Okay. And the quasi-Newton method is also very nice as compared to the Newton method. It is more efficient. So, and this method of Newton's is even faster than gradient descent. All right. This variant of Newton method with Armijo is even faster than the gradient descent. Okay. So don't always think that gradient descent is the efficient one, because I know that in all of the lectures and all people tell about gradient descent. But actually, if you come to a numerical method class, you will hear that there are more algorithms efficient than gradient descent. So gradient descent is not the ultimate goal. There is something more than gradient descent, like gradient descent with Armijo. So two things you have to take from this two lectures is gradient descent can be improved by putting the Armijo condition. Second, you can put Newton's method with Armijo condition and it is far better than the gradient descent. These are the two take home message. Okay. All right. So just the summary before we look into the problem. Like let's look into a problem. I ask you to solve by hand and by computer. Okay. So now we know this method. I will not derive this method. Derive how this method is coming. Okay. How you can come from here to here. Okay. There is a very nice derivation, but we'll not look into this. Just know that this is the formula for this, and try to see like using computer programming that actually it takes less number of iterations. I will give you two assignment problems today, which are very important. Okay. Make sure you do it by yourself. Make sure so that you can appreciate that about this method. Okay. You can see how a very hard nonlinear problem can optimum to its optimum just within 4 iteration of Newton's method. Just within 4 methods, you can easily solve by hand. Okay. I don't think like in a complicated function, you had a method previously before this class. Okay. Anyway, so let's solve this problem. Again, we look into our favorite function, minimum f of xy. Okay. And you know what it is, x square plus 2y square minus 2xy minus 2x. I am taking this example again and again because You already know how this looks for different values of right hand side. It's just like ellipses as you increase the values. Okay, and you know already which is the minimum point. So just the same example I'm taking with different methods. Okay, so you minimize this function and apply the Newton's method, but I have not given you two other information. What are those information? That is the initial guess. Okay, what is the initial guess you can take? X0, maybe x1, 1. Okay, and take h equals to 1. All right, and try to solve this using the method we just derived here. So can you tell me what is grad f? Grad f, yes, grad f. Hmm? Can you solve this and tell me, let me know soon. Grad f you find and the Hessian del 2f. After you find del 2f, there is more to it. What is more to it? After you find del 2f, you have to find del 2f inverse. Because del 2f inverse is here. Del 2f inverse is like the same as finding inverse of a matrix. And this is a two-dimensional function, isn't it? It involves x and y. So what should be the matrix size of the Hessian or the gradient? Like Hessian, at least you tell. What should be the size of the matrix size of the Hessian? This is where you should exercise. Hmm? So, del 2f, it can't be a scalar, right? Because gradient is itself a matrix. Gradient is a column vector. Dou f by dou x, dou f by dou y. 2 rows, 1 column. Del 2f will be also known as the Hessian. You know, it's a symmetric matrix and it's a 2 by 2 matrix here because you will have dou f by dou x, you will also have dou f by dou y. You don't have dou f by dou z, right? So it will stop at 2 by 2. So you know that the Hessian will be a 2 by 2 matrix. For 2 by 2 matrix, you can easily compute the inverse. For 3 by 3 matrix, computing inverse is very hard. For 2 by 2, you already know the formula. Okay. Can you compute grad f and grad f del 2f inverse?